Thanks everybody for joining. I'm Len Hampton. John McNamara is going to be our host from the Sodick side, and I'll let him make introductions. But it's nice to have you all back. Looks like we got a fantastic crowd. Thanks for taking time out of your day. I think it'll be beneficial for everybody for sure. So, John,
Yeah,
thank you.
thanks, Len. I'm gonna give it a minute or two here to let everyone kind of continue to filter in. But we'll start with some introductions. My name's John McNamara, as Len mentioned. I've been with Sodick Plus Tech for a little over 2 years now on the sales side, and cover various territories around the country, Minnesota and New England, and a little bit of Illinois as well. Um, and then we have Bennett Howard here as well. Um, he's also one of our sales guys, been with the company for, what is it, Bennett, almost 7 years at this
Yeah, I
point?
think 7.5 years. Yeah, thanks, John. I'll just quickly, I see some of my customers on. Thanks for joining, guys. I covered another sales territory in some of the Midwest, Michigan, Milwaukee, and then kind of focused on the West Coast right now, Southern California, Utah, some different medical hotspots. So I see some of you on here. So thanks for joining. I'm excited to learn myself. Go ahead, John.
Yeah, thanks, Bennett. Yeah, so a little bit about Sodick and Friends, this webinar series we started during COVID to kind of just keep the conversation going with some of our partners and, make sure that we're all staying engaged. And that was very successful for us. We were doing about one a week at the time, and we're bringing it back here towards the end of this year. We're going to shoot for about once a month. So stay tuned for more information on the next one. And we hope you enjoy this Sodick and Friends webinar as well. I will now turn it over to Sheldon Alexander. He's our partner from HUSKY, and he will be the presenter today talking about hot runner balance in the mold qualification process. Sheldon?
Thanks, guys. Welcome, everybody. Thanks to the Sodick team for inviting me to speak to you guys. This is a pretty exciting topic, one that's near and dear to my heart. That's using hot runner balance in the mold qualification process. As John mentioned, my name is Sheldon Alexander. Been with HUSKY for 28 years. Started out as a service technician, worked my way up to service manager, and now I am in business development and key account management. So let's get started.
And well, real quick, Sheldon, before you start, I just wanted to explain to everybody how the Q&A portion will work. So there is a Q&A tab at the top of your screen. You'll be able to see throughout the presentation. If you have questions, type those questions in there. At the end, the last 15, 20 minutes or so, we'll go over those questions. I'll read them to Sheldon, and we can kind of get some of those answered for you. So if you want to use that throughout the presentation, go for it. And we'll see you then. I'll give it away to Sheldon here. Thanks.
Okay, one second, guys. I stopped sharing for a minute. Let me bring that back. Okay, should be all set. All right, so balance. What's balance? So balance is simply the difference between the heaviest and lightest part in a multi-cavity tool. Today, we're going to focus specifically on short shot balance and short shot balance that's used during the mold qualification process. Questions that we will attempt to answer today are: what are some of the factors that influence short shot balance, and how do you measure balance, specifically the procedure that is used in the industry today? And then finally, balance expectations. So hot runners can certainly help in the balancing process. When improving injection molding balance, hot runners can assist in fine-tuning the balance process. There are many websites and publications dedicated to why balance is important. That's not something I'm going to cover today, but let's just say it is important. There is little or no information in what is an acceptable balance level, or more importantly, what procedure one should use in verifying short shot balance. And this is going to be the focus of this webinar today. So why is balance important at the mold qualification process? Well, it's important to give us the largest potential process window, especially when we're dealing with complex, thin wall, highly tolerance parts. What we can see if the mold is not balanced, we can get things like overpacking in certain cavities, dimensional instability, not just shot to shot, but cavity to cavity. But as I said, balance is an important tool, and it's an important variable when qualifying a mold. So what factors influence short shot balance? So first we start with the machine. So the machine certainly has a large impact on it, whether it's the tonnage, tonnage distribution, or the amount of tonnage itself, processing, so injection profile, melt preparation, cooling time, shot size, for sure the resin, the mold, and of course the hot runner system. So these are all things that can contribute to the overall balance of a system. For sure, the hot runner, as I said, the geometry, the shear effects, the thermal profile, the gating style, whether it's a hot tip or a valve gate. And I will go into each one of these variables in greater detail in the coming slides. So here's an example how the process can affect the balance. So in this application, it's a 32 cavity syringe barrel mold. And most customers, most machine suppliers out there, they send the signal to open the valve stem at the same time you start injection. And what that causes is that causes the stems to not open all the way, at least not all of them, before you start injecting. And that can lead to imbalance. On this example here, we simply adjusted the stem timing, either delayed the injection or opened the stem early. One of the variables I like to use is basically mold touch. So when the mold closes and it touches before it builds tonnage, you send a signal to open the stem. That gives the stem about half a second or so to open before you start injection. As you can see in this example, the short shot balance changed from 60% to 90% by simply adjusting the stem open timing. As I said, you can delay the injection or you can open the stem early. Either one allows the stems to all open before you start injection. This example, I wanted to speak a little bit about the resin. So in this application here, we're running a PC ABS system using the same mold, the same machine, the same process. The balance was about 65%, again, using PC ABS. Switching out to polypropylene, again, same machine, same mold, same process, except for temperatures. Polypropylene runs at a lower temperature than PC ABS, but all other variables being the same. As you can see, the balance improved from 65% to 93%. And this is an example how the resin can have an impact on balance, specifically if the resin is shear sensitive. Any styrenic base resin, whether it's polystyrene, ABS, any of these resins that's shear sensitive, that's thermal sensitive, will have a fairly large impact on the overall system balance. For sure, the hot runner and the controller can have a large effect on the balance of the system. So things like thermal uniformity, precise temperature control, and I'll just touch on the controller a little bit, just because there's a lot of controllers on the market. Some of them are very good, some of them are not so good. But the way to look at a controller is like if you're trying to reduce the light level in a room, there's a couple of ways to do that, right? So first way is to turn that light on and off, let's say every second. So you turn it on for a second, you turn it off for a second, you turn it on for a second, you turn it off for a second. That's one way to get 50% light into that room, but it's not the most optimal way, right? The most optimal way is using a dimmer switch that cuts the power by 50%. So that's a good analogy for the different types of controllers out there. What you want to do is make sure you have a controller with PID, ideally PID squared, that can give you that accurate temperature control. The algorithms are tuned for the different zones. With any hot runner system, a tip zone is very different from a manifold zone, for example. So the type of control, the PID variables are very different from those two types of zones. So precise temperature control is important. Synchronized valve gate. So type of hot runner, whether it's a thermal gate or a valve gate, certainly has a large effect. And then within the valve gate category, if it's a synchronized plate actuated system or an individual system, and I'll explain those differences in greater details in the coming slide. So the most common types of hot runners in the industry today is what we call a thermal gate. I would say this probably makes up about 70% of the hot runners in the industry today. It certainly was the original hot runner that came out 40, 50 years ago. It's a fairly simple system. There isn't a lot of moving parts. After injection, so during the hold stage, plastic begins to solidify in the gate. Combination of hold time, coolant time, that plastic freezes in the gate, creates a plug. When the mold opens, it separates from the gate, creating what we call vestige or a belly button type situation on the part. That height of that gate vestige could be about 1/3 to 1/2, maybe even 2/3 of the gate diameter, depending on the resin, depending on the process. So that the mold opening, like I said, breaks that junction. Some of it remains on the part, some of it remains in the gate. What remains in the gate acts as a frozen plug to prevent resin from drooling into the cavity while the mold is opening and the parts are being injected. On the next cycle, you need to push that frozen plug into the part. If you have a multi-cavity tool, let's say an 8, a 16, a 24, even a 32 cavity, those plugs are not all going to blow at the same time. They're going to blow independently, and there's going to be some plugs that blow first, some that blow second, and then some that blow much later on. That blowing of those plugs or those gates will give you inconsistency or balance issues. So you're not just going to see imbalance within one cycle, but you're going to see inconsistency from one cycle or the other because of this phenomenon of having to blow that plug on every thermal gate. Next, we have valve gates. So valve gates was the next gen hot runner system that was invented. So first we had thermal gates, and like I said, that's still the majority of the hot runners in the industry today. But next came valve gates, and the valve gates works on a simple principle. Instead of relying on a thermal shutoff to freeze that gate, we rely on a mechanical means of closing that gate. So basically you have a valve stems. You got a valve stem that opens and closes. So before injection, the valve stem opens, and that allows resin to flow into the cavity. After injection and hold, the valve stem closes, pushing the stem forward to close that gate mechanically. As you can see, that plug blow phenomenon in the previous slide doesn't exist with a valve gate system. So naturally you get better balance with a valve gate system versus a thermal gate or a hot tip system. Next, I have here an example of a hot tip versus a valve gate. So again, as the previous examples, everything stayed the same. Same mold, same resin, same machine, same process. First, we ran it as a hot tip. And you can see with the hot tip system, the variation was about 0.44 grams, or the balance was about 70%. Simply removing that valve gate and removing that hot tip and replacing it with a valve gate, the balance greatly improved. We went from 70% balance with the hot tip to 93% balance with the valve gate. And the procedure that we use, and I'll talk more about the procedure in the next few slides, but just as a point of reference, the procedure that we use was a 90% short shot balance. So again, hot tip, 70% balance, valve gate, 93% balance, significant improvement. So as I mentioned, not only do you see in a cycle, you see inconsistency cycle to cycle on a hot tip versus a valve gate. So on this graph here, on the bottom, the two lines on the bottom, the red and the black, those are two valve gate shots. And as you can see, the part weights are charted on that graph, and you can see they're very similar. You know, from a mathematical standpoint, the correlation is 0.995. That indicates near perfect symmetry or near perfect correlation between those two shots. And again, that was a valve gate system. Above that, we have two shots from a hot tip system. And just visually, you can see the yellow line and the darker line, how different they are. And then if you look at it mathematically, the correlation is only 0.377. So weak correlation between one shot on the next on the hot tip system, strong correlation between one shot on the next on the valve gate system. And this is typically what we see with a hot tip versus a valve gate system. And again, that's primarily due because of that plug blow phenomenon that I mentioned earlier. So let's talk about valve gates a little bit. So as I said, valve gates are growing in popularity in the industry, specifically in the medical market. I would say, you know, as I said, overall, hot tips are about 70% of the market. Within the medical segment, I would say valve gates are probably 70 to 80% of the market. So the primary types of valve gates in the industry today is individual piston valve gate configurations. And basically what that means is that each valve stem has its own piston and cylinder, and they move independently of each other. One of the issues that arises from that, as I mentioned earlier, is not all the stems open at the same time, and that can cause imbalance, but also not all the stems close at the same time. And with small parts, specifically parts that Sodick machines are known for, small, high precision parts, that inconsistent closing can have a dramatic effect on the dimensional stability of the part. And I'll explain that a little bit in the next slide. As a result of that, the medical industry pushed us to develop a plate actuated system. And with that system, as you see on the right side of the screen, all the valve stems are attached to basically an ejector plate. And then that ejector plate is what's moved back and forth. That ejector plate can be moved pneumatically or hydraulically, but the optimal way to move that plate is with servo. And again, I'll talk about that in the next coming slides. Excuse me. So as I mentioned, not just in stem opening, but in stem closing, again, on very small, highly technical parts that has tight tolerance in, the valve stem closing can have an impact on this. And let me explain why. So the majority of the valve gates out there, it's what we call a plunger shutoff. That means that the valve stem is straight, and that goes into a hole into the gate detail. And usually there's a land. That land is anywhere from, I would say, 0.3 millimeters to maybe 0.5 millimeters in height. And the gate diameter is usually about 1 millimeter. So when that valve stem closes, you need to push that 0.5 millimeter by 1 millimeter cone of plastic. You need to push that into the part. And that is essentially packing. And if those stems are closing inconsistently, it's going to affect the dimensions. And again, I'm talking small, highly technical parts and resins. In this application here on the top, this is a 32 cavity system. The customer suspected that the valve stem closing inconsistently was contributing to the dimensional variability that they were seeing. So what we did is we outfitted the hardener with proxy sensors. So we knew, so we know when the valve stem closes, when each individual valve stem closes. And not only did we see a range of dimensional dimensions across this one feature on the part, but we were able to find correlation between when the stem closed versus the dimension. So we converted the system over to a plate actuated system, synchronized stem movement. And as you can see, the dimensional range dropped from 0.14 millimeters to 0.04 millimeters. And this reduced the scrap rate by 25%. So pretty dramatic improvement on this specific part because of the valve stem closing variation on a individual piston versus a synchronized valve stem movement system. So what I have here, some of the other factors that can improve or can affect short shop balance. Some positive, some negative. So plate actuation for sure. So a plate actuated valve gate system, that for sure gives you the best balance performance on a short shot. The higher percentage of fill, meaning how much resin you put in the mold when you check balance. Is it 80? Is it 85? Is it 90? Or is it 95? That determines your balance number as well. The more material you put in the mold, the better the balance is going to be. And the reason for that is that the first to fill cavities slow down filling as the plastic gets to the back wall and allows those cavities that's lagging to catch up. So the higher percentage of fill, the better. And like I said, I'll talk about that specifically in the next couple slides. The higher the cavitation, so certainly higher than a 24 drop, or a 24 cavity system, whether it's 32, 48, 96, or 144, the higher you go in cavitation, the more likely that the balance is going to degrade as you go up in cavitation. Stack tool, for those of you that's familiar with stack molds, we do see some difference between the clamp side and the injection side, again, because of the sprue bar in the stack mold. So with a conventional mold, or with a single face mold, carriage forward pressure is pushing against the hardener or pushing against the A side, and it doesn't affect the B side. It doesn't affect the clamp tonnage. But on a stack mold, that carriage forward pressure is pushing on the center of the mold. And what that means is that the A side is being relieved of tonnage, and the B side or the clamp side is being supplemented with the carriage forward pressure. So we do see some imbalance between the A side and the B side, or the injection side and the clamp side on stack molds because of that phenomenon of carriage forward pressure being applied to the center of the mold. Side gate. For those of you that's familiar with side gates, so side gates is a subcategory of thermal gates, and usually you have multiple gates on the same nozzle housing. That certainly has a negative impact on balance. And the reason for that is that you have multiple gates on one nozzle housing, and the first gate that pops will fill, and it has to get to a certain point, build up a certain level of back pressure before the other gates on that drop will blow. So you can expect a degradation of balance on a side gate versus a standard thermal gate. Thermal or shear sensitive resins, as I also already mentioned, polystyrene, ABS, nylon. These are resins that we see more imbalance issues with. And then, of course, a poor temperature controller. So these are all things that can affect short shot balance performance, some positive, some negative. So let's talk about how do you measure balance. So I would say there is a couple methods that I see in the industry. And the first is a first to fill. So on a first to fill method, what you're focusing on is that first cavity to fill. So on any multi-cavity tool, whether it's a 2 cavity or 144 cavity, there's always one cavity that fills first. As I said, that is your focus. So you want to adjust, excuse me, you want to adjust your whole pressure and your whole pressure down to near zero. You either want to keep your hold time or move your hold time to cool it. Okay. And then you want to adjust your transition point between first stage and second stage so that first part is where you would like it to be. So an example of this is, let's say, 90% fill. So many customers I speak to, their procedure is first to fill 90% of the final part weight. Variations on that is 95 or 80 or 75. So any percentage really, but again, your focus is always on that first to fill part. So let's say you want that first to fill part to be 90%. As I said, you adjust your transition point so you can achieve that. In my opinion, this procedure is best used for troubleshooting. So I use this procedure if I'm troubleshooting an issue. Let's say it's a part sticking issue. Let's say it's a dimension issue. Let's say it's an ejection issue. Any issue with the molded part or with the mold, or even the machine and the hot runner. Any one of those issues that I'm trying to troubleshoot, I will use this procedure, and I will go down to 50, 60, 70% fill. So I get an exaggerated view of the balance or the imbalance of the system. And then I try to correlate that to the issue that I am troubleshooting. So again, let's say you're troubleshooting part sticking issue. You do a balance test. And what you're looking for is correlation between the sticking issue and the imbalance. So let's say it's a 24 cavity tool and you have sticking issues with cavity 2, 15, 16, and 22. When you do the short shot, you want to see if there's any correlation to the issue you're seeing, which is sticking, and to the actual results of the short shot. And I find the most accurate way to compare that is in Excel. So you can put those two data sets, and then you can use what they call the Pearson correlation factor within Excel to compare those two columns, and it will tell you, let me just go back a couple of slides so I can show you guys. 1 second here. So it will give you correlation number here. So the value you get will be between -1 and 1. -1 and 1 means perfect correlation, meaning the short shot imbalance is a direct indicator of the issue you're troubleshooting. It doesn't mean it's the root cause, but it's a strong indicator that you should be looking at that. So that's 0 to 1. As I said, that's near perfect correlation. -1 to 1. As you get closer to 0, that means weak correlation. So above 0.8, strong correlation. Below 0.5 is weak correlation or no correlation. Let me move forward here. So as I mentioned, this is the first to fill method. I would say this is I'd say probably about 60 to 70% of the customers I speak to, they use some variation of this procedure. The second procedure is what we call a percentage of fill. So on the first example, we were focused on that first to fill part being a certain percentage of the full part. With this method, percentage of fill, is you're looking at the entire shot size, and you want to put a percentage of the entire shot size into the mold. So let's go through the example. So the same thing, you reduce the pressure to near zero, you move the hold time to coolant time, or you leave the hold time as is, and you adjust your transition point, right? Same as the first. But what you're looking for here is the total shot weight. So let's say it's a 48 cavity tool with a 5-gram part weight. Full shot is 5 grams, okay? So 48 times 5, that's 240 grams. 90% of 240 is 216. So you want to put 216 grams into the mold. So you do a short shot using the method, as I said, and you measure all the 48 parts until you get close to 216, as close as possible as you can get to 216. And then you go ahead and you measure the parts and you compare the heaviest to the lightest, and that gives you your balance number. I prefer to use this method during the mold qualification process, and I like to use it at 95%. So I will do 95% as a percentage of fill, and that's where I will check my balance. And the reason I do that is that that is as close as possible to what you're going to do in production, right? So RJG and all the other guys that teach scientific injection molding, they talk about doing your transition from 95 to 98%. 95% is a nice number. It gives you, it's at the bottom of the range from scientific injection molding. And that tells you what the balance looks like as you're going from first stage to second stage. So this is the method or the procedure that I would recommend for mold qualification. So as I mentioned earlier, the amount of resin you put into the mold when you measure short shot has a direct impact to the balance results, right? So the graph that you see there, the graph on the right-hand side of the screen, you have percent imbalance, and then you have shot size, so the amount of resin that you're putting into the mold. And what you see is that the lower the amount of resin, the higher the imbalance. So at about 10%, the imbalance is about 45%. But as you continue to put resin into the mold, that balance improves, as I said, because the first to fill cavity slows down, basically checks up, and allows the lagging cavities to catch up. So the amount of resin you put into the mold, whether you use the first to fill method or the percentage of fill method, it doesn't matter. The amount of resin you put in is going to have the biggest impact on the balance number that you see. So it's important that you pick a procedure and a percentage consistently. So you're not comparing apples to oranges. So here is an example of how procedure has an impact on the balance results. So this is a 2x32 stack mold, and I ran a few different balance numbers. So the first, all the way to the left, is a full shot. So full shot, this is fully packed out parts, production parts. The balance is about 98%, which is considered very good in the industry. On a 95% fill, the balance is 93%. On a 95% again, two different methods, right? One is fill, one is first to fill. So on the fill, you're putting 95% of the shot weight into the mold. On the first to fill, you're putting 95% of the fullest part into the mold. And you can see the difference, 93 to 89. But here's the thing, precision is important as you get up, because a very small amount of additional material or less material into the mold will have a dramatic effect on the results. And you can see it by the last two columns on this graph on the right-hand side. So the first one at 89% balance was done at 95.1. You round that off, that's 95%. And then the next one was done at 94.5. Again, you round that off, and that's 95%. So you can see the difference in results. One is 85% balanced, one is 89% balanced just by rounding errors. So it's very important that you control the amount of resin you put in the mold very precisely, because that has a very large impact on the results. So one of the questions I ask customers is, why do we do short shot balance? And the answer I get back, if I can summarize, is that the industry believes that short shot balance is a good predictor of full shot balance. Okay. So the first to fill cavity, some of the things I hear from customers is the first to fill cavities is going to get more hole pressure and potentially have different dimensions, potentially wear the parting line more versus the last to fill cavity. But I find this experiment that I do almost on every balance situation that I come up across, I find this to be very interesting, and that is what you see here. The yellow is short shots using first to fill 95%. So that's what you see with the yellow line. And then the red line is full shot balance. Okay. What is interesting is that the correlation is weak, almost non-existent. What that means is that the first to fill part on the short shot is not the first to fill part on a full shot, meaning there is weak or no correlation between a short shot and a full shot. So I think the data needs to be taken with a grain of salt when you're doing short shot testing. So let's talk about balance expectation. As I said, this was one of the questions I hope to answer in this webinar, is what's an appropriate balance expectation? And I would say the first step is to determine what procedure is right for you. There is no right procedure. There is no wrong procedure. I talked about two procedures, first to fill and percentage of fill. But as I mentioned, there is many different subsets of those procedures. As I said, there is no right procedure. There is no wrong procedure. You just need to pick a procedure that's right to you and keep that procedure consistently across all your molds. At Husky, we would recommend the percentage of fill and 95% for the reasons I mentioned in the slides before. Once you pick the procedure, then you need to determine realistic expectation for that procedure. So for a valve gauge system, we would expect it to be 90% balanced using the 95% percentage of fill procedure that I would recommend. So on a valve gauge, 90. On a hot tip, 85% balance. And as I mentioned a few slides ago, there are factors that could both positively affect these numbers and negatively affect these numbers. So let me give you an example. If you have a 12 or an 18 cavity or even a 24 cavity valve gauge system that's plate actuated, I would expect the balance to be higher than 90. If you have a 96 cavity individual pistons, I would expect the balance to be a little lower than 90. And same with the thermal gates, right? If you have a stack mold, if you have a side gate, I would expect the balance to be lower than 85. So these are your baseline numbers using this procedure. But as I said, there's other factors that could positively or negatively affect the results. So first step, determine what procedure is right for you. Second step, determine a realistic expectation for that procedure. Meaning, if you want, that's fine. As I said, there's no right or wrong, but you cannot realistically expect 90% balance on a valve gate or 85% balance on a hot tip using an 80%. That's not realistic. So the question I get often is, okay, if I went through the process of picking the right procedure for my company and picking realistic expectations for that procedure, sooner or later, you're going to come upon a mold that doesn't meet that expectation. It might be 1 in 10, it might be 1 in 25. And the question is, what do I do in those cases? And what I say to customers is that you shouldn't stop the mold qualification process. You should proceed with the mold qualification process. Record the imbalance that you're seeing, record all the other factors in the mold that makes up for a successful mold qualification, whether that's dimensions or ejection or cycle time, anything like that. And if you find an issue, go back and see if there's correlation to the balance. If there is no correlation to the balance, then go on and troubleshoot that issue. But if you have no issues with the mold qualification, meaning the mold hit cycle time, the part quality is what you expect it to be, there's no ejection issue, no issues like that, but the balance does not meet your expectation, my recommendation is to record it and move on with putting that mold into production. I see too many customers fighting with the balance of a system for weeks, if not months, when it doesn't affect the part quality. It doesn't affect anything related to the mold. It's a checkbox in the mold qualification process that customers feel necessary to check. As I said, I think we need to be pragmatic about it. And again, if it's not affecting the system performance, record it, move on. So what I have here is an example of using the balance in the mold qualification process using the procedure that I recommended, which is that 95% of fill. So this is a 144 cavity hot tip system. And initially, the yellow line is the initial results of the imbalance or the balance results. And you can see it was about 67%. Okay, well outside the customer's expectation. The expectation was above 90%. So we did some troubleshooting, and what we found is contamination in the tips, which I'm sure you guys are not unfamiliar with. Any new mold startup, whether it's a new machine or a new mold or a new hot runner, there's potential for contamination, especially with a hot tip, right? The gate's very small, usually sub 0.8 millimeters. Or less than 36 thou in diameter. Then we have a tip in the middle of that. So you basically have a choke point. Any amount of contamination gets collected in that area, and it affects it. So we cleaned the tips, latched the cavity plate over, cleaned all the tips, cleaned all the contamination, and the balance went from 67 to 85. It basically went from the yellow line to the dark line. Sorry, no, let me take that back. The original was the dark line. The first cleaning was the red line. What we saw is that, yes, the balance improved, but there was still a couple cavities that were lagging behind, right? And what we surmised is that contamination might be in the hot runner in the manifold itself. So we end up sending the hot runner back to us. We got it cleaned, and that balance improved to 93%. So you can see how using the method that I suggested on an extreme system like this, which is a 144 cavity hot tip system, does work in identifying potential issues in the hot runner, in the mold, in the machine, or even in the process. So to summarize here, factors that influence short shot balance on any system, a lot of customers I speak to, they feel that it's strictly the hot runner that contributes to that, but it really is the entire system. So starting with the machine, the tonnage, the flatness or parallelism, the levelness of the machine, the screw design, what percentage of the barrel we're utilizing. And this is, one of the benefits of Sodick machines is that they have relatively small injection units, as well as the two-stage injection units that they're known for, where the plastification of the resin is separated from the injection of that resin. That gives you better shot control. It gives you better repeatability, and it gives you better balance. So the type of machine, barrel utilization, screw and barrel design, these things all affect the balance. Processing, injection profile, how well you're melting that resin or preparing that resin, back pressure, things like this, cooling time, shot size, these all affect the balance of the system. The resin, of course, as we talked about, the type of resin, the quality of the resin, how well it's prepared, is it dried properly, etc. The mold, for sure, can have a large impact on balance, cavity to cavity, geometry, consistency, gate diameter, L dimension, cooling layout, how many loops are in the mold. I can't tell you how many mold trials I go to where you have one in on cavity number 1, and it cycles through all 32 cavities and comes out on cavity 32. Well, guess what? The temperature of cavity 32 is very different than cavity 1, right? So you want to make sure the cooling layout is appropriate. You have appropriate Reynolds number. The delta temperature between the inlet and the outlet is as low as possible. I like to see 1.5 degrees Celsius or lower. The lower the number, the better. That tells us the cooling efficiency. The Reynolds number is where we want it to be. Part geometry, something we didn't talk about a whole lot, but the example I like to use is a closure, right? So you guys are familiar with both with closures, where you have the closure itself and you have the Tampa evident band. A lot of the Tampa evident band is injection molded, meaning they're not slit or cut afterwards. They're molded into the part, but that basically acts as a gate. So if you do the balance before the Tampa evident band, it will usually be worse than if you do it after the Tampa evident band, because the Tampa evident band acts as a gate. It acts to slow down the first to fill cavities and allow the last to fill cavities to catch up. It allows the pressure in the mold to equalize, right? So the part geometry certainly plays a large role in the balance number. Type of mold, is it a family mold? Is it a stack mold? The stiffness of the mold, the stiffness of the hot runner, and of course the stiffness of the machine, as I already mentioned. Venting, consistency from one cavity to cavity, also has a large impact. Certainly the hot runner has a large impact to the overall system balance, the geometry, the shear rate, the thermal effect, the heater layout, cooling layout, certainly valve gate versus hot tip, the plate design, and the temperature control. So these are all the factors that go into determining what the short shot balance is on any tool that you see out in the industry. So in summary, short shot balance is an important tool that can be used during the mold qualification and troubleshooting process, specifically if you're troubleshooting an issue. There are many different procedures that can be used to check short shot balance with varying results on the same system. So it's important to pick the right procedure for you. And to make sure that procedure fits your needs and matches and match your expectation to that procedure. So thank you guys. We'll open it up to Q&A session. My contact information is on the screen. You guys feel free to reach out to me if there's any questions that I don't get to in the next few minutes.
Well, yeah, thanks, Sheldon. Great job. Very interesting stuff. Go ahead, and if you have any questions, type them into the Q&A portion, and I'll start reading those, and hopefully we can get to all of them. I'll start off with one of the first ones. Have you come across instances of unbalance within a single nozzle, and what tips or and multiple tips side gating? If yes, what is the likely percentage?
Yes. So a side gate thermal gate system is particularly challenging for us, especially the more the more gates you have on that side gate. So it can range anywhere from 1. So if it's a 1 gate side gate, I would expect the results to be very similar to any thermal gate, but it can go to 2, 4, and even 8 tips on a nozzle housing, as the question said. And again, it depends on I hate to say it depends, but it depends on the resin and the application, depending on the procedure. I would expect the balance to be anywhere from 70 to 90% using a 90% first to fill procedure on a side gate system.
Okay, thank you. I'll go on to the next one. What is your procedure for calculating the 95% total shot?
So let me go back quickly here. So the procedure I would use is what I have on the screen here, which is let's say it's a 48 cavity tool. Let's say the full part weight is 5 grams. So the total shot weight. So if you weigh all the parts, you set up the process to make production parts. You collect a shot, you weigh it. It should be 240 grams. If you're using a 90%, then you're looking at 216 grams. So again, you adjust your shot size, sorry, not your shot size, your transition point until all 48 parts weigh 216. So that is what I would do to get you that 90% percentage of fill. If it's the previous procedure, which is the first to fill procedure, it's a similar exercise, but you're not looking at the full shot weight. You're just looking at the first to fill part. So again, if you assume the part is 5 grams on a full shot, you want 90% of that, or 4.5 grams. You want the first to fill part to weigh 4.5 grams.
Okay. Do you recommend artificial balancing the parts by adjusting the HR temps on the tips as needed? For example, raise the temp or the tip temp for the lower filled parts.
I love this question. I absolutely love this question. In my experience, I don't see a need to do that, right? So I don't like doing that because, one, I don't think it's necessary. So this is what I would say to you is collect short shots without adjusting the tip temps, collect full shots without adjusting the tip temps, measure the full shot part weight, measure all the dimensions on the full shot, again, using all the tip temperatures the same, and then go ahead and adjust the tip temperatures and do the same thing again. And whenever I have done this, one, I have seen very little positive result of doing that. Meaning, yes, you might be able to affect the short shot balance by adjusting the hot runner tip temperatures, but it has no impact on the full shot balance, and it has no impact on the dimensional stability of the part. So that's the majority of times I see that it has no impact. So why would you do it if it has no impact on the final production parts? That's one. Two, in some cases, less than 10% of times, I actually see it has a negative impact on the final part quality, whether that's weight, consistency, or dimensional consistency. So I would go through the exercise, but I think you will find there isn't a need to do that. There is no need to adjust the tip temperature.
Okay, thank you. Is there a rule of thumb for how often you should clean hot tips and or the hot runners? Do you have any experience with how PCR compares to virgin resin?
Yeah, good question. So PCR, let's talk about PCR first. So I would say PCR, which is a hot button topic in the industry right now, right? Sustainability is a big thing in the industry right now. So a lot of customers are looking at PCR, specifically PET PCR, because there's a lot of PET on the market, and there's a lot of PCR PET on the market. So first is the cleanliness of the PCR, right? So at the top of the list is chemical recycled, which is they unzip the molecule and rezip the molecule. You know, lack of technical details there, but it's a chemical process that is as clean as you're going to get, and it should perform no differently than virgin resin. But at the bottom of the list is simply regrind, where you get resin, you grind it up, and you reuse it. Those resins can have a lot of contamination. And what you want to do if you're using those resins is you want to make sure you're using as big as gates as possible. I would definitely recommend valve gates because that would give you a much bigger surface area for contamination to flush out and not clog the tip. To answer the question, I would performance is going to tell you when you need to clean the hot runner, meaning as balance deteriorates, as performance deteriorates, that's an indication that there's contamination in the hot runner, and you need to clean it. I don't think there is a periodic or an established time that I would say, you know, every 6 months or every year. I would say let the performance tell you if you need to clean the hot runner. So that's PCR. What we do see with some resins, some colorants, some additives in the field is that we see it plating out. So some component of the resin plates out and accumulates like plaque in the arteries in the melt channels of the hot runner and or the tip area of the hot runner. And the surefire way to see that happening is to monitor your injection pressure and see if that increases over time. Once that increases more than 10%, that's an indication we have plaquing going on in the hot runner somewhere, and you need to get that hot runner cleaned. So I would say, you know, 10% increase in injection pressure, that is that you don't have a reason for. You didn't change the resin, you didn't change the process, but the pressure went up. That's an indication that you need to get the hot runner cleaned in a fluidized bed. You know, basically bake it out.
Okay. Got another one here. If it is a hot to cold runner, should the balance study be modified or the same procedure be followed?
Not a good question. So what I like to do with hot to cold is I like to do two balance studies. One with all the plastic coming out of that drop, meaning all the parts from that drop plus the runner compared to all the drops. Okay, so that's procedure number one. The second procedure I would use is just focus on the parts itself. So forget the cold runner, just focus on the parts. First, look at the balance within one runner, and then look at the balance across the entire tool. So those are the two ways I would look at balance in a hot to cold application.
Okay, thank you. I think we'll get one more in here. Where do you get the 1.5 degree delta between cavity water temp from? Is there a chart or paper that shows the turbulent flow efficiency I can look at other than a Reynolds formula?
Good question. Good question. Honestly, I'm not sure. So Reynolds numbers, yeah, there's lots of charts and graphs that shows you ideal Reynolds number. That 1.5C is something that I have always used, and I know many people at Husky uses that 1.5C as a rule of thumb. Let me do some digging and see what material there is to support that. And I can send it out to the group. But really good question. Really good question.
All right. I guess we'll get one more in here. I got one last question. For first to fill, how do you measure when a part is 95%, 90% fill, while the part is still being molded?
So this is the procedure. This is the first to fill procedure on the screen. So
Yeah.
the first thing you would do is you would make production parts. So set up the process, set up your pack and hold, make good parts, let's say. Okay. You weigh those parts, and you will get an average. The average should be fairly close, 98, 99% balance on a full shot, right? So you get an average of all the part weights, and it should be about, let's say for this example, it's a 5 gram part. So your average is about 5 grams. Okay. If you're doing a 90% first to fill, then you want to target 4.5 grams on the first to fill. So you zero off your hole pressure and you leave your hole time as is, or you move it to coolant time, and you collect a shot. And you weigh all the parts, you find the heaviest part of that shot, and let's say it's 4.8 is the heaviest part. Well, your target is 4.5 because you want 90%, right? So then you move your transition point up a little bit and you do it again. And you keep doing that until the first to fill part is as close as possible to 4.5. And that's how you go about determining, what's the right procedure for that 90% first to fill procedure.
Okay. Well, thank you, Sheldon. I thought you did a great job. If you guys have more questions for Sheldon, reach out to him directly. I'm sure he'll be happy to answer some of those questions for you. Yeah, thanks again for everyone joining. Len, I don't know if you wanted to say a few words.
Yeah, I do. Sheldon, do you have your back page, maybe a contact page? Maybe people can take a snapshot to ask you any questions directly, or
Yep.
make
Yeah, there you go.
first contact. I'm sure most people know you already, but I'm sure there's a few that need to take a quick snapshot of this. But thanks. That was a fantastic presentation for sure. And all the folks out there, good questions. Really good. Looking forward to maybe Husky 2, right?
Yeah. And if I remember correctly, Len and John, you guys will upload this webinar onto your YouTube channel. So if you guys want to go back and look at it, it's something that you can do.
Yeah, YouTube,
Correct.
social media, our website, all the above. Thanks, folks. Have a good rest of the afternoon, and all the best.
Yeah, and
Awesome, guys.
stay tuned for information about the next Sodick and Friends coming up in the new year.
Thanks, John. Sheldon, pleasure.
Thanks, guys.
Bye, guys.